Right. So today we'll start the applications. What are the applications of N-type and P-type semiconductors? Okay. Applications of N-type and P-type semiconductors. Okay, where we actually use them, right? So in applications, students, combination of N and P, you can combine one N, one P, or you can combine three. You can combine three of these. You can combine, right, by combination of many extrinsic semiconductors. Okay, we are going to those combinations have lot of applications. Okay, in electronic components. Okay, so first let me just introduce what is called a diode. What is a diode? Diode is a combination of one N-type semiconductor and one P-type semiconductor. Okay, so if I combine, let me just draw like this. Okay, if I combine one N-type and one P-type semiconductor, if I join, it is not joining, just for understanding purpose I am saying like this, but it is there is a method to prepare. Okay, so if you take the combination of one N-type semiconductor and one P-type semiconductor, that combination is what we call is called a junction. It is called a P-N junction, right? If I connect this to a terminal of battery and this to another terminal of battery, okay, if you make electrical connection, right, or if you connect with the wires, we call this arrangement as a diode, so that you can pass current to this, or you can get current, right, by different manners. This is basically called diode. Diode is nothing but combination of a P-type semiconductor and an N-type semiconductor. Okay, and you know very well, in N side, electrons are majority carriers. In N-type semiconductor, electrons are majority carriers and holes are minority carriers. Whereas in the P side, holes are majority carriers, and electrons are minority carriers. Okay, so this is the basic setup for a diode. Diode means combination of one P-type and one N-type semiconductor. Okay, what is the use of this? Where we are using this? Listen, diodes are used, right, in many electronic equipments for different purpose. Okay, diodes are used as rectifiers. Diodes are used as rectifier. What is a rectifier? Rectifier will convert alternating current into direct current. Okay, rectifiers are device, okay, which convert AC into DC, alternating current into DC current. You know very well, in our home, from the plug point we get AC current actually, but most of our instruments, say our laptop, right, or any TV, LED TV or LCD TV, whatever it is, most of our equipments require DC current. What we get from plug point is AC. Okay, therefore every equipment must contain a rectifier. What it will do? It will convert the AC current into DC current. For the conversion of AC to DC, we use diodes. Okay, then not only for this, we have other applications. Number 2, diodes are used as photo detectors. photodetectors. Okay, yeah, if you shine light, okay, the junction diode will convert that light energy into electrical signal, okay, and that electrical signal is measured. Based on that, what type of radiation that falls on the material, that you can identify, and you can find the energy of the radiation, right? Okay, so it's a very important one in industry, right? Photo detectors. What type of radiation is falling on a material, right? That we can identify, whether it is IR or a visible radiation or ultraviolet radiation, right? So here basically what happens, the radiation energy, right, is converted into electrical signal, okay, is converted into electrical signal. That electrical signal is detected, and based on that, what type of radiation falls on the material, that you can find. Okay, then apart from this, we have many applications. I'm just showing only few. Okay, you might have heard about LEDs, LED, right? LED materials and lasers. Okay, what is LED? Light emitting diodes. Students, all of you switch on your camera. Your camera should be in on mode always. Okay, now what is LED? Light emitting diode. Light emitting diode. See, in this you just give electric current, or just give current, or apply electric field to a diode. The diode will emit radiation, usually light. The diode will emit light. All our LED TVs, right, it consists of huge number of LEDs on the screen. So whenever electricity is passed, okay, it will give different lights. You will get different colors. Okay, so LED is light emitting diode, where we are using diode. Okay, we are using diode in this type of devices. What is laser? You know very well, light amplification by stimulated emission of radiation. In laser also we use diodes. Okay, diodes are used in lasers. Not only that, diodes are also used in solar cells. You might have heard about this, solar cells. Okay, the solar radiation, right, is converted into electricity, right? Here we convert solar energy or solar radiation is converted into, right, current or electricity. We get current by converting the solar energy, right, by using what is called a device called a solar cell. That solar cell device consists of diodes, basically diodes. Okay, so by the combination of a p-type and n-type semiconductor, right, we can make many devices actually: rectifiers, photodetectors, LEDs, lasers, solar cells, etc., etc. Okay, so all these devices, right, they consist of basically they consist of diodes. Okay, so remember, this is very important. Then second one, suppose if I take three semiconductors, 2n 1p or 2p 1n, like that, we call them as transistor. Let me write in the next page. So the second one is transistors. Transistor. What is a transistor? Transistor is contains three extrinsic semiconductors. Okay, it consists of three extrinsic semiconductors. So in transistors we have two types of transistors. Okay, one is NPN transistor, 2n semiconductor. Okay, between this we have a p-type. We have three layers. The middle layer is actually the p-type, and the bottom layer, top layer and bottom layers are N type. It is called NPN transistor. Okay, just understand like this. I have a material which has 3 component. Okay, the upper one is N, lower one is N, middle one is P. Right? We have emitter, base, and collector junctions. Right? One semiconductor acts as emitter, the one acts as a base, the other one acts as a collector. You are going to learn all these things in physics. I am not going to discuss much about that, but I am going to give you just the basic ideas, right? Just elementary ideas. Transistors, we have 2 types of transistor. One is NPN, the other one is PNP transistors. In PNP, middle layer is N, top layer and bottom layers are P type. In NPN, middle layer is P, top layer and bottom layers are N type semiconductors. Okay, so a transistor consists of 3 extrinsic semiconductors, okay, combined, and you will get 2 junctions here. Between NP we have 1 junction, between PN we have another junction. So transistors consist of 3 extrinsic semiconductors and 2 junctions. Okay, right? What is the use of these transistors? Where we use? Transistors are used as amplifiers. Transistors are used as amplifiers. Right? Nowadays we have a lot of improvement, right, in the transistors. We have field emit transistor, we have MOSFET, we have a lot of things. Okay, ரொம்ப develop பண்ணிட்டாங்க. These are all basic things I am just giving you. Okay, amplifiers. Transistors are acting as amplifiers. What they do? They will amplify the signal. They will amplify the signal. What is mean by that? Okay, it will amplify radio signals. It will amplify audio signals. Right? It will amplify. It will increase the signal intensity. Okay, amplifying means it will increase the intensity of the signal. That's all. Right? So transistors are used as amplifiers. Transistors consist of 3 extrinsic semiconductors, either NPN or PNP. Okay, students, apart from this we have other improved version of these transistors are also available, called FET, field effect transistor. We also have MOSFET. Okay, these are all latest transistors we are using in electronic equipments. Okay, yeah. But these are all basic ones. These are all basic ones, and these are all modern transistors that we are using in electronic equipments. Okay. What is the purpose of transistors? Simple. Transistors amplify the signal. That's all. Okay. So these are all the applications, some of the applications of N-type and P-type semiconductors. Okay. Then, now let me go to the next important one. Apart from these semiconductors, okay, apart from these semiconductors, there are certain transition metal oxides. Right? Transition metal oxides. Students, observe this carefully. Some transition metal oxides, they have conductivity. Okay, they show conductivity almost close to the conductivity of metals. Listen, some students, kindly turn on your camera. Kindly, I want to see your face. Yeah. Yes, everyone, turn on your camera. Yes. Some transition metal oxides, not all, some transition metal oxides, okay, some transition metal oxides, they have conductivity close to the conductivity of metal. Okay, for some transition metal oxides, conductivity, electrical conductivity, right, conductivity sigma means electrical conductivity. Conductivity is close to the conductivity of metals. You know very well, metals are having very high conductivity, right? They are all good conductors. But some transition metal oxides, right, they have conductivity close to the conductivity of metal. Okay, yeah, this is very, very important. Lot of research is going on, okay, nowadays, to synthesize or to fabricate these oxides and to produce modern devices. Okay, people are doing a lot of work in this. Right, which are all the transition metal? I'll give some few examples here. Right, some transition metal oxides examples: titanium oxide TiO, chromium dioxide CrO2, and rhenium trioxide ReO3. Right, these oxides, right, they have very high conductivity. Their electrical conductivities are close to the metals. Okay, especially this rhenium trioxide, it shows conductivity close to copper. You know very well, after silver, I had told you already, silver has the highest conductivity among metals, right? Next to silver is copper. This rhenium trioxide conductivity is close to copper. Okay, so you can call these oxides as conductors. This rhenium trioxide can be called as a conductor because conductivity is extremely high. Okay, this is a very important one, keep this in mind. Then some other transition metal oxides like vanadium monoxide, vanadium dioxide, okay, vanadium trioxide, and titanium trioxide. Okay, these metal oxides, right, they show metallic as well as insulating properties. Okay, you can use them as insulator, right? You can insulate metals, right, or you can insulate the material using these oxides. They are used as insulating materials. Basically, they are used as insulating. They have insulating property, so we use this as insulating materials for some devices. Okay, this is another important point you should keep in mind. Right? Yeah. So with this we have completed the applications of N-type, P-type semiconductor, and this is not a semiconductor actually. Students, listen carefully. This is not a semiconductor, but these oxides are very special oxides. They show conductivity in the range of metals. Okay, that is why these oxides are discussed separately. Okay, very, very important. Keep this in mind. Then now we'll start the last part of this chapter, that is magnetic properties. Magnetic properties of solid. Magnetic properties. Okay, I have told you in the beginning, if you want to measure or if you want to study any property of the material, what we have to do, we should apply some effect, okay, on the material, and we should see the response. Okay, so if you want to study the magnetic properties of solids, what we have to do, place the solid. Okay, suppose I want to study the magnetic property of some solid. What you have to do, place the solid in a magnetic field. in a magnetic field and measure the response. Measure the response of the material. How the material respond to the applied magnetic field. Okay. So based on the response that we get, we classify the solids, right? See, we are keeping in a magnetic field. In a magnetic field, how the solid respond. Based on the response of your solid in a magnetic field, we classify solids basically into 5 types. We classify the materials into 5 types. How solids respond to the external magnetic field. Okay, right? So what I'm saying, actually, you take the magnetic field. This is north pole, let this be south pole, and place your solid inside. This is your solid. Okay, apply the magnetic field and see the response of the solid. Okay, based on the response, okay, we classify the solids into different types. What are the different types? Number 1, diamagnetic solid, diamagnetic solids, paramagnetic solids, ferromagnetic solids, ferromagnetic solid, antiferromagnetic solids, antiferromagnetic solid, and the last one, ferrimagnetic solid, ferrimagnetic. Okay, so based on the response of the solid in the external magnetic field, we classify the solids into 5 different types: diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic. Okay, now before going to see these different types, right, what I do is how material interact with the magnetic field, external magnetic field. Listen, in atom, students, you know well, in atom we have nucleus and electrons. Okay, we assume like this, right? Based on the Bohr model, we assume that electrons, right, electrons will revolve around the nucleus. You know very well, electron carry charge. Electron is a charged particle. Whenever charged particle moves, right, in a fixed orbit, what we'll get a current. And you know very well, wherever current is there, magnetic field will be produced. Wherever electric field exists, there exists a magnetic field. So this electron, this circulation of electron will produce what is called the magnetic field. Okay, we call this motion as orbital motion. This motion is called orbital motion. So electrons, right, in atom, electron in atom, okay, undergoes orbital motion. Orbital motion. Electrons also undergo spin. What is spin? Spin is if this is the electron will revolve, or the electron will spin about its own axis. So this is the axis of spin. So the electron spins about its own axis. This motion is called spin. Okay, whether electron make orbital motion or spin motion, right, both will produce what is called magnetic field, and that magnetic field is measured by a quantity called magnetic moment. We measure the magnetic field of the magnetic field produced by electrons, or magnetic field produced by the material, okay, the overall magnetic field, right, we measure by a quantity called magnetic moment. Okay, magnetic moment, we give the symbol mu for magnetic moment. The symbol for magnetic moment is mu. Students, observe this carefully. Why material, okay, exhibit or interact with the external magnetic field? Because the material itself has some magnetic field. Every material has some magnetic field. How the magnetic field arises in a material? It is because of the electrons. Basically electrons. Okay, electrons in atoms, they show two kinds of motion. One is called orbital motion. Orbital motion means electron revolving around the nucleus. Just imagine like that. Electrons revolving around the nucleus is the orbital motion. And these electrons also have the property of spinning. Spinning means it is revolving about its own axis. It is not revolving, actually it is spinning about its own axis. Okay, so electrons have two types of motion in the atom, orbital motion and spin motion. Both these motions, okay, will produce magnetic field. Okay, to quantify the magnetic field, we are using a term called magnetic moment. Magnetic moment is given a symbol, okay, mu, right? This is the symbol we use for magnetic moment. Students, listen carefully. The magnetic moment produced by the material or by the electron, okay, if you take a single electron, the magnetic moment associated with a single electron is extremely low. Okay, let me just give the point to the next page. See, what I'm trying to say is that magnetic moment mu associated with an electron, this is extremely low, is extremely low, very very low. What's the value? The value for magnetic moment of electron, right? Let me write this as mu e. Magnetic moment associated with the electron, this is very very low, is of the order of, okay, the value is in the order of 10, okay, I'm sorry, let me write this. The magnetic moment associated with a single electron, okay, is very very low, and the value is and the unit, I'm sorry, the magnetic moment, right, magnetic moment associated with the electrons are extremely low. So they usually measured in the unit of Bohr magneton. Okay, what's the unit we use? The unit is Bohr magneton. Magneton. Okay, remember why we are using the unit Bohr magneton? Because one Bohr magneton right, one Bohr magneton for electron mu e is equal to 9.27 into 10 to the power minus 24, very 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 low, ampere meter square. Or you can also write this as, okay, the Bohr magneton associated with electron. Okay, Bohr magneton associated with electron. Just to avoid confusion, I'll put mu b. Bohr magneton. Okay, so Bohr magneton associated with electron can also be given as 9.27 10 power minus 24. Okay, joule per Tesla. Joule per Tesla. Tesla is the unit of magnetic field. Tesla is the unit of magnetic field. So 9.27 10 power minus 24 ampere meter square. You can give in the ampere meter square, or you can also write in joule per Tesla. This is actually one Bohr magneton. And remember students, the magnetic moment of the material, the unit of magnetic moment is Bohr magneton. Remember why we are using Bohr magneton unit? Okay, before that, listen. How to calculate magnetic moment? Students, listen. Suppose I'll take some solid, right? I'll keep the solid in a magnetic field and I'll measure the magnetic moment of the material, right? Magnetic moment, spin only magnetic moment, I'm going to take only spin. Spin only magnetic moment can be calculated using this formula, n into n plus 2, and this value is expressed in the unit of Bohr magneton. Magnetic moments are expressed in the unit of Bohr magneton. Okay, what is one Bohr magneton? One Bohr magneton is an extremely low value, 9.27 into 10 power minus 24 ampere meter square or joule per Tesla. Okay, this is the unit of magnetic moment is Bohr magneton. Remember, unit of magnetic moment is Bohr magneton. This formula is applicable for spin only magnetic moment. Magnetic moment arises due to spin motion of electron. Okay, not orbital motion. Okay, if you come to higher classes, right, you will learn, right, the other magnetic moment, right, how to calculate the magnetic moment produced due to other motions, right, orbital motion and the total magnetic moment will do, right, in higher classes. But for you this is sufficient. Okay, spin only magnetic moment. Okay, this is very important, students, keep this in mind. Let me repeat again. See, in magnetic property, if you want to study magnetic property of your material, what you have to do, place the material in the magnetic field and measure the response. Okay, based on the response we classify. Response means your material will show magnetic field, or your material will behave like a magnet. Okay, and it has some associated magnetic field associated with the solid, right, is measured in the quantity called magnetic moment, right. So based on the response we classify solid into 5 types. Okay, and how the magnetic field is originated in your solid. How the magnetic field is originated in the solid? It is because of the electrons, basically electrons, right. In atom, the electrons present in atoms, they have 2 kinds of motions. One is orbital motion, the other one is spin. Okay, both these motions are responsible for the magnetic field of the material. Your material has magnetic field, it is because of these motions. Okay, and these magnetic field that arises in the solid is measured by a quantity called magnetic moment, which has the symbol, which is expressed by the symbol mu, right. And the next important point is magnetic moment associated with an electron, right, is extremely low, right. And magnetic moment is expressed in the unit of Bohr magneton. What is one Bohr magneton? One Bohr magneton is 9.27 into 10 power minus 24, extremely low quantity. Okay, so we express magnetic moment in the unit of Bohr magneton. Magnetic moment is expressed in the unit of Bohr magneton. Keep this in mind. Why? Because magnetic moment values are extremely low. That's the reason. And here I have given a formula. This formula will give you magnetic moment due to spin alone. Spin only magnetic moment. Okay, our magnetic moment arises out of spin of the electrons. Is it clear, students? Any doubt? Students, is this clear?
No doubt, sir.
Yeah, very good, ma. Good. Now, okay, we'll proceed further. Now we'll discuss these materials, right? What is meant by diamagnetic material? What is meant by paramagnetic material, right? In what way, on what basis we classify these materials, right? We'll discuss that. Okay. So first let me take diamagnetic material. What is a diamagnetic material and how it responds, right? What is the response of the diamagnetic material in the external magnetic field? So number one, diamagnetic solid. As our topic is solid, I'll use the name diamagnetic solid. Students, listen carefully. Suppose if you take some solid, keep it in a magnetic field. If the solid is repelled by the magnetic field, okay, right, we call the solid as a diamagnetic solid. I repeat, you take a solid, keep it in a magnetic field. If the solid is repelled by the magnetic field, we call that solid as diamagnetic solid. So diamagnetic solids are weakly repelled by the external magnetic field. External magnetic field. Why? What is the reason? The reason is the magnetic field arises in the solid. Students, listen carefully. Suppose I'll take a magnet. This is external magnetic field. Say this is north pole, this is south pole. Okay, and assume that this is the direction of the magnetic field. Magnetic lines of forces. Okay, magnetic lines of forces, right, exist in the magnet, external magnet. Now, if I keep the solid in the magnet, okay, I'm going to keep some solid in the magnet, it's a solid, right, due to the magnetic field. Listen, magnetic lines of forces, right, I'm just showing in this direction. When you place the solid in a magnetic field, your solid will get, or will some magnetic field is arised in the solid. That magnetic field, suppose if the direction of the magnetic field is exactly opposite to the direction of the external magnetic field. See, this is the lines of forces of external magnetic field. Now the magnetic field arises in the solid. This is our solid. It is opposing the external magnetic field. Whenever the magnetic field generated in the solid opposes the external magnetic field, then it is repelled. Okay, we call this type of solid as diamagnetic solid. Diamagnetic solids are weakly repelled by the magnetic field. Okay, when a solid will show this type of behavior, when you keep it in a magnetic field, it is opposing when it will oppose if all the electrons in the atom, right, are paired, right, if all electrons are paired, all the electrons in the solid or atom, all the electrons exist as a paired electrons. That means there is no unpaired. That's the meaning. No unpaired. There is no unpaired electrons. Okay. If all the electrons are fully paired, then the magnetic field arises in the solid will oppose the external magnetic field. Okay. We call those materials as diamagnetic material. Right? In the diamagnetic material, right, magnetic moment is 0. Let me write here. Magnetic moment is 0 in net magnetic moment. We can say net. Net means both spin and orbital. Okay, combined, right? Combined net magnetic moment or net magnetic moment is actually 0 in the case of diamagnetic materials. Okay. So remember, in diamagnetic materials there is no unpaired electron. Okay, all the electrons are fully paired. Whenever you have fully paired electrons in atoms present in the solid, then the material will produce a magnetic field. That magnetic field will oppose the external magnetic field. Okay, that's the point. Keep this in mind. Right? Okay, now I'll give some examples for diamagnetic substance. Examples. Yes, we have a lot of examples. Okay, sodium chloride, H2O, water molecules, right? Benzene, C6H6. Okay, We have many examples actually. Lot of examples also are there. Right? The idea is simple. There should not be any unpaired electron. There should not be any unpaired electron. All the electrons should be paired. Those materials are called as diamagnetic solids. Is this clear, student? Any doubt? Okay, good. Then the second kind of substance is paramagnetic solid, when we call a solid as a paramagnetic solid. Let me write here. So second one is paramagnetic solid. Paramagnetic solid. Paramagnetic solid. When we can call a material as paramagnetic material. Very simple. Listen, you take the material or you take the solid, place it in a magnetic field. If the material is weakly attracted, attracted by the external magnetic field, okay, you can call the material as paramagnetic. It is weakly attracted. Diamagnetic material is weakly repelled, whereas paramagnetic materials are weakly attracted by the magnetic field. Okay, and here these materials are magnetized, okay, in the same direction of the magnetic field. What is meant by that? Listen, I have told you. See, suppose if this is north pole, south pole, if this is the direction of the magnetic lines of forces in the external magnetic field, if I place the solid, let me place it here itself. Let me place the solid here. If the solid, listen, the moment you place the solid in a magnetic field, the solid get magnetized, and the magnetic field of the solid, if this magnetic field arises in the solid also facing in the same direction, okay, then this material get attracted. See, in the previous case, the material generate magnetic field, and that magnetic field opposing the external magnetic field. That is why diamagnetic materials are repelled. Whereas in paramagnetic material, okay, the magnetization arises in the same direction. Therefore, it is attracted. Okay, and the moment you remove the magnet, okay, just remove the magnet. The moment you remove the magnet, immediately, right, the magnetic moment starts to align in different directions. Therefore, net magnetic moment becomes 0. Immediately it will lose the, right, the moment you remove the magnet, that is, you are removing the solid from the magnetic field. If you remove it, immediately, okay, the solid, okay, immediately the solid will lose, okay, the magnetism. Immediately the solid lose the magnetic field or magnetism. See, when you place the solid in the magnetic field, it is get magnetized. Okay, these arrow mark actually indicate direction of the magnetic moment. Let us not go into the details. It is, I'll use the term like this. It is get magnetized. That magnetic magnetization is in the same direction of the external magnetic field, so it is attracted. When you remove the magnet, the moment you remove the magnet, immediately the solid will lose the magnetism. Okay, that is the important property of paramagnetic solid. If you place the solid in the magnetic field, the material get magnetized and it is weakly attracted by the magnet. The moment you remove the magnet, the material immediately lose the magnetism. It will come to the original substance like. Okay, it will become a original substance. Is this clear, student? And remember, these material, paramagnetic materials, contains one or more unpaired electrons. Paramagnetic solids contains one or more unpaired electrons. Unpaired electrons must present. Therefore, they have some net magnetic moment. Magnetic moment is not zero here. They have some net magnetic moment. Okay, because when you place it in the magnetic field, they get magnetized, and the magnetic field is in the same direction of the external magnetic field. Therefore, the material will have some magnetic moment. Okay, and remember, paramagnetic materials contain at least one or more unpaired electrons. At least one unpaired electron should be there. Okay, examples. Let me give some examples here. Actually, lot of examples are there, but I am going to give you only few. Listen, this molecule O2, the molecule O2, oxygen molecule, you might have learned this, the molecular orbitals of oxygen molecule in your lower class, where you may find that oxygen molecule has two unpaired electrons. O2 molecule has two unpaired electrons. Therefore, oxygen molecules are paramagnetic substance. It is weakly attracted by the magnet. Okay, O2. Then copper 2 plus ions. Okay, cupric ion. Copper 2 plus means cupric ion. Fe3 plus means ferric ions. Chromium 3 plus ferric ion, chromium 3 plus ions, right? And other examples, etc., etc. These are all few examples for materials showing paramagnetic character because they have unpaired electron. Okay, suppose I'll take copper. I'll show you how many unpaired electrons are there. For this, you must know the electronic configuration. Simple. Listen, copper atomic number is 29. 29. So the electronic configuration, if you see, you'll get 1s2, 2s2, 2p6, then 3s2, 3p6. Okay, so here we have 10 electrons, here we have 8 electrons, so total 18 is over. Okay, then 3d10. Okay, here we have 28 now, 28 and 4s1. This is the electronic configuration of copper. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1. This is the electronic configuration of copper. Now what I am going to do, Cu2 plus means you should remove 2 electrons. Remove 1 electron from this, remove 1 electron from this. 4s orbital has only 1 electron, remove it. And remove 1 electron from 3d10. I have 10 electrons here, remove 1 from this. So what we'll get? You'll get 1s2, 2s2, 2p6, 3s2, 3p6 and 3d9. 3d9. This is the outer electronic configuration. This full configuration. 3d9 is outer. This 3d subshell has 9 electrons now. Students, observe carefully. I am talking about cupric ion, not copper. Cupric ion has 9 electron in the d subshell. You know very well d subshell has 5 orbitals, right? D subshell has 5 orbitals. 5 orbital. Now you arrange the electrons 1, 2, 3, 4, 5, 6, 7, 8, 9. Now see, I have an unpaired electron here. This is an unpaired electron. Unpaired electron. All these are paired. These are all paired electron. I have one unpaired electron in Cu2 plus ion. Remember, for a material to behave like paramagnetic, at least one unpaired electron should be there. So cupric ion has one unpaired electron. Okay, so it will act as paramagnetic material, right? Similarly, if you take iron, ferrous, Yes, yes, students.
Sir, even 4s1 is unpaired, sir.
Yeah, 4s1 is unpaired, but this is metal, pure metal. Pure metal. In metals, magnetic character is decided by, it's not only decided by the single electron, it is decided by other things. Okay, because this electron become free in metals. In metals, this electron, this one electron become free electron. Okay, in metal, so it can move freely everywhere, and we have lot of free electrons will be there. Okay, if you take a material of copper, you take a solid of copper which consists of so many copper atoms, there are so many unpaired, one electron in s orbital will be there. All these s electron will come out and form a free electron gas. These free electron gas have different behavior. Okay, it does not act as an unpaired paramagnetic substance. That's the point. It will act it will act in an entirely different manner. I will discuss that later. Okay, I will discuss that later. Why we are not choosing copper here? We will discuss. Copper 2 plus, it has one unpaired electron, so it acts as a paramagnetic substance. For metals, though unpaired electron is there, yes, your question is correct. Copper has one unpaired electron, no doubt in that. But since it is a metal, okay, neutral metal, for neutral metal, the unpaired electron sometimes behave in a different manner. Why and what is the reason, we will discuss. Similarly, now I will take iron. Iron atomic number is 26. So the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6. So here we have 18 electrons. Then 3d6, 4s2. 3d6, 4s2. This is the electronic configuration of iron. Now I am going to remove 3 electrons. Okay, let us take Fe3 plus. Fe3 plus means we should remove 3 electrons. Remove 2 electrons from this and remove 1 electron from this. So I will get 1s2, 2s2, 2p6, 3s2, 3p6, and this becomes 3d5. Now we have 5 electrons in the d subshell. You know very well, d subshell has 5 orbitals. Okay, fill up these 5 electrons. 1, 2, 3, 4, 5. Now see, all the 5 electrons are unpaired electrons. So there are 5 unpaired electrons. There are 5 unpaired electrons present in Fe3 plus ion. Therefore, ferric ion acts as paramagnetic substance. Ferric ion is paramagnetic. Okay. Similarly, here cupric is paramagnetic. I am not talking about iron. Iron also has unpaired electron. Okay. In D6 we have unpaired electrons. But since it's a neutral metal, students listen, neutral metal sometimes behave in a different manner. Okay, just because they contain unpaired electron, you should not say that they are paramagnetic. No. Because of the presence of unpaired electron, they may behave in a different manner. We'll discuss that as we go along. Okay, good. So this is regarding paramagnetic solids. Okay, then the next one. And remember, paramagnetic solid has net magnetic moment. It is not zero. They have net magnetic moment. They contain one or more unpaired electrons. Right? Then the third category. Okay. Before going to that, listen, for paramagnetic substance, you can calculate what is called spin only magnetic moment. You can calculate mu s. Spin magnetic moment. How? What is the formula? Formula is this: n into n plus 2 Bohr magneton. Bohr magneton is the unit, and here n is the number of unpaired electron. What is n? N is the number of unpaired electrons present in one atom. Okay, that's the meaning. So if you take Cu2 plus, in Cu2 plus, right, we found that there is 1 electron present. Let me show that. Yeah, here. In Cu2 plus, see, we have 1 unpaired electron. So for Cu2 plus, n equal to 1. It has one unpaired electron, so n equal to 1. If I put n equal to 1 here, then the spin only magnetic moment for Cu2 plus is square root of 1 into 1 plus 2, which is nothing but square root of 3. Square root of 3 is 1.732 Bohr magneton. This is the spin only magnetic moment of Cu2 plus ion. Okay, if you know unpaired electron, you must know how to calculate the spin only magnetic moment. Remember, student, magnetic field arises not only due to spin. I have told you in the beginning, electrons, okay, in atom, they give magnetic field in two ways. One due to orbital motion, the other one due to spin. Here we are calculating magnetic moment for the spin motion, for the spin of the electron. Okay, right? Net magnetic moment means it is the total, that is orbital plus spin. Okay, if you take the total, you will get net magnetic moment. Here I am giving you only the spin, right? How to calculate spin only magnetic moment. Similarly, for Fe3 plus, can you calculate what's the value for Fe3 plus? How many unpaired electrons are there in Fe3 plus? Just now we discussed. How many unpaired electrons are there in Fe3 plus?
5, sir.
Yeah, so n equal to 5 in this case. N equal to 5. If n equal to 5, what's the value? Use this formula.
Root of 5 into 5 plus 2.
5 into 5 plus 2. What's the value? 5 plus 2 is 7. 7 into 5. 5 plus 2, 7. 7 into 5 is 35. Root of 35, anyone? Can you give roughly? Rough value? Root 36 is 6, right? Root 36 is 6. Root 35? 5.8 something, right?
5.9, sir.
Yeah, it will be close to 5.9. 5.8 or 5.9 like that. Okay. And remember, see here, if the n value is 1, then spin only magnetic moment is in the range of 1 point something. If n value is 5, spin only magnetic moment is in the range of 5 point something. So if spin only magnetic moment is available, you can say that how many unpaired electrons present. Suppose a material has spin only magnetic moment of 2.82. What does this indicate? Some material has spin only magnetic moment 2.82. What does this indicate?
2 or 3 unpaired.
No, not 3. If it is 3, the value should be 3 point something. Okay, don't round off the value. Okay, don't round off. Right? 2 point something, whatever may be the something. Okay, it may be 8.8, 2.9, whatever it is. Right? It consists of 2 unpaired electrons. Okay, if there is 3 unpaired electron, spin only magnetic moment will be 3.8 or 3.9 it will go. You should not round off the value. Don't round off. Okay, whatever number is present in front of the decimal point, okay, that gives you the number of unpaired electrons. But there are some exceptions there, some exceptions also there, but usually this is the idea, right? Is the concept clear, students? Any doubt? So what is a diamagnetic substance? Anyone?
No unpaired electrons.